Hello there, and welcome to the Sleepy Library. Tonight, we are drifting through the story of our home, Earth. The pale blue dot that floats through space, carrying every story, every breath, every moment of everything we have ever known. This is not simply a collection of facts. It is a journey through deep time, through oceans and stone, through the quiet architecture of the only planet we know that breathes with life. From its molten beginning to the delicate balance that sustains us now, Earth has been shaped by forces both gentle and catastrophic, building a world stranger and more beautiful than we often remember to notice. If you enjoy these quiet journeys into wonder, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Let the weight of the day fall away. Allow your thoughts to settle like sediment drifting to an ocean floor. Let's begin. Earth formed from a cloud of dust and gas around 4.54 billion years ago. In the beginning, there was no Earth as we know it. Only a swirling disk of particles orbiting a newborn sun, fragments left over from the sun's own formation. Gravity pulled these fragments together, slowly at first, then faster as larger clumps attracted more material. Dust grains stuck to dust grains, pebbles collected into boulders. Boulders crashed together to form planetesimals, rocky bodies that grew kilometre by kilometre through endless collisions. This accretion continued for tens of millions of years, building mass, building heat, building the foundation of everything that would come. The young Earth was nothing like the world we know. It was a molten sphere of rock and metal, its surface a sea of magma glowing red and orange under a sky thick with steam and volcanic gases. Meteors rained down constantly, each impact adding more material and more energy. The planet had no solid ground, no oceans, no atmosphere fit for breathing. It was a furnace world, spinning through the dark, slowly cooling, slowly settling into layers as heavier elements sank toward the center and lighter materials floated toward the surface. This was the Hadean Aeon, named for Hades, the ancient underworld. It was Earth's infancy, violent and inhospitable, yet already following the patient laws of physics that would one day allow forests and rivers and quiet nights beneath the stars. The Moon was born from a collision that nearly destroyed Earth. About 30 to 50 million years after Earth began to form, another planet-sized body struck it. This object, sometimes called Theia, was roughly the size of Mars. The impact was catastrophic. It vaporized both crusts, sending enormous plumes of molten rock and gas spiraling into orbit. The heat was intense enough to melt stone. The force was enough to tilt Earth's axis. From the debris cloud that remained, the Moon slowly coalesced, gathering fragments that would never fall back to Earth. This collision fundamentally shaped our planet's destiny. It gave Earth its 23-degree axial tilt, which creates the seasons we experience. It left Earth with a large iron core, denser and more magnetically active than it might have been otherwise. And it gave us the Moon, whose gravitational pull would go on to stabilize Earth's rotation, slow its spin, and create the tides that shape our coastlines and influence the rhythms of life. The Moon is not just a companion in the sky. It is a piece of Earth's history, a reminder written in stone that our planet was forged through cosmic violence and has been shaped by chance encounters across deep time. Today, the Moon drifts slowly away from us, about 3.8 centimeters each year. But for billions of years, it has been our steady partner, lighting the night, pulling the oceans, keeping Earth's climate stable enough for life to flourish. Earth's core generates a magnetic field that shields us from solar winds. Deep beneath the surface, nearly 3,000 kilometers down, lies Earth's outer core. This layer is made of liquid iron and nickel, heated to temperatures that rival the surface of the Sun. As Earth rotates, this molten metal flows in vast currents, driven by heat rising from the even deeper inner core. These movements of electrically conductive liquid create Earth's magnetic field through a process called the geodynamo. The magnetic field extends far out into space, forming an invisible shield called the magnetosphere. This shield deflects most of the charged particles streaming from the Sun in what is called the solar wind. Without this protection, those particles would strip away Earth's atmosphere, molecule by molecule, leaving the surface exposed to harsh radiation. Mars, which lacks a strong magnetic field, lost much of its atmosphere this way billions of years ago. Earth's magnetic field has reversed many times throughout history. The north and south magnetic poles have flipped positions hundreds of times over hundreds of millions of years. These reversals are recorded in rocks that formed at mid-ocean ridges, where new seafloor is constantly being created. As molten rock cools, magnetic minerals within it align with the prevailing magnetic field, freezing that orientation in place. By studying these patterns, scientists have pieced together a history of magnetic reversals stretching back millions of years. The field does not flip suddenly. The process can take thousands of years, during which the field weakens and becomes more chaotic, before re-establishing with reversed polarity. We do not know exactly why this happens, but it seems to be linked to changes in the flow patterns of liquid iron in the outer core. Some evidence suggests the frequency of reversals may be influenced by plate tectonics, as cold slabs of oceanic crust sink deep into the mantle and alter the temperature and flow dynamics at the core mantle boundary. The magnetic field is not stable, even between reversals. It wanders and weakens in different regions. Currently, the North Magnetic Pole is drifting from northern Canada towards Siberia at an accelerating rate. This movement is tracked carefully because it affects navigation systems and must be accounted for in everything from smartphone compasses to aircraft guidance. The magnetic field is part of what makes Earth habitable, a quiet guardian generated by processes deep within the planet, reminding us that even the ground beneath our feet is alive with motion. The oldest known rocks on Earth are over 4 billion years old. In the remote wilderness of northwestern Canada, in a place called the Acasta Gneiss Complex, lie some of the oldest rocks ever found on Earth. They date back about 4 billion years, formed when Earth was still in its violent youth. These ancient stones are metamorphic, meaning they were once other types of rock that were later transformed by intense heat and pressure. They have survived countless geological upheavals, mountain-building events, and erosion cycles. That they exist at all is remarkable. Most of Earth's early crust has been recycled back into the mantle through plate tectonics, melted down and reformed many times over. The rock record gets sparser the farther back we look. For the first 500 million years of Earth's history, we have no rocks at all, only tiny mineral grains called zircons, found embedded in younger rocks. Some of these zircons are over 4.4 billion years old, making them the oldest known materials on Earth. These minuscule crystals, each smaller than a grain of sand, are incredibly durable. They resist weathering and can survive being melted and recrystallized. Inside them, scientists have found chemical signatures suggesting that liquid water existed on Earth's surface far earlier than once thought. If true, It means oceans may have formed within just a few 100 million years of the planet's birth, as soon as the surface cooled enough for water vapor to condense. The ancient rocks and zircons tell us that Earth's surface was already complex and active early in its history. Continents were beginning to form. Water was present. The stage was being set for life. Earth's oceans formed as the planet cooled and water vapor condensed. The origin of Earth's water is one of the great questions of planetary science. Some of it likely came from volcanic outgassing. As Earth's interior heated and differentiated, volatile substances, including water, were released from the rocks and erupted to the surface through countless volcanoes. This water vapor, along with carbon dioxide and other gases, accumulated in the atmosphere. Other water may have been delivered by comets and meteorites, icy bodies from the outer solar system that bombarded the young Earth during its formation. These impacts could have brought significant amounts of water, along with organic compounds, adding to the inventory of volatiles already present. As the surface gradually cooled, the thick atmosphere of steam began to condense. Rain fell. It fell for thousands, perhaps millions of years, filling the low-lying basins in the newly forming crust. By about 4 billion years ago, Earth had its first oceans. These early seas were different from today's. They were likely warmer, more acidic, and enriched with dissolved minerals from volcanic gases. But they were oceans nonetheless, vast bodies of liquid water covering much of the planet. The presence of water changed everything. Water shapes landscapes through erosion and sedimentation. It moderates temperature. It participates in chemical reactions that alter rocks and atmosphere. And most importantly, water became the medium in which life would eventually arise. Today, about 71% of Earth's surface is covered by ocean. The vast majority of Earth's water, about 97%, is in the oceans. Another 2% is locked in ice caps and glaciers. Only about 1% is fresh water in lakes, rivers, and underground. A tiny fraction, less than 0.001%, exists as water vapor in the atmosphere at any given time. Yet, this atmospheric water is essential. It drives weather, distributes heat, and brings rain to the land. The water cycle, the endless movement of water between ocean, atmosphere, and land, is one of the fundamental processes that makes Earth a living planet. Plate tectonics continuously reshapes Earth's surface. The ground beneath our feet feels solid and permanent, but Earth's crust is broken into large pieces called tectonic plates that float on the semi-molten mantle below. These plates move slowly, driven by convection currents in the mantle and the pull of dense oceanic crust sinking back into the interior at subduction zones. The movement is measured in centimeters per year, about as fast as fingernails grow. Yet, over millions of years, these motions reshape the entire planet. At mid-ocean ridges, new crust is born. Magma wells up from the mantle, cools, and solidifies, pushing older crust away on either side. This process, called seafloor spreading, creates new ocean floor and gradually widens ocean basins. At subduction zones, old oceanic crust bends downward and slides beneath another plate, descending into the mantle where it melts and is recycled. These zones are marked by deep ocean trenches and are often sites of intense volcanic activity and earthquakes. When plates collide, mountains rise. The Himalayas, the tallest mountain range on Earth, formed from the collision of the Indian and Eurasian plates beginning about 50 million years ago. The collision continues today, and the mountains continue to rise, though erosion wears them down at nearly the same rate. When plates slide past each other, They create transform boundaries marked by earthquakes, like the San Andreas Fault in California. Plate tectonics does more than move continents. It regulates Earth's climate over geological timescales by cycling carbon between the atmosphere, oceans, and rocks. It brings nutrients from the deep Earth to the surface, enriching soils and fueling ecosystems. It creates diverse habitats, from high mountain peaks to deep ocean trenches, increasing opportunities for evolution and biodiversity. And it prevents the planet from becoming geologically dead, maintaining a dynamic, self-renewing surface unlike anything seen on other rocky planets in our solar system. Mars is geologically inactive. Venus may have some volcanic activity, but nothing approaching the complexity of Earth's plate tectonics. Only Earth, with its particular combination of size, temperature, and water content, has maintained this process for billions of years. Continents have drifted across the planet throughout Earth's history. 200 million years ago, all of Earth's major landmasses were joined together in a single supercontinent called Pangaea. If you stood on its shore and looked inland, you could, in principle, walk from what is now South America to Africa to India to Antarctica without crossing an ocean. Pangaea was not the first supercontinent, nor will it be the last. Earth's continents have repeatedly gathered and dispersed in a cycle lasting several 100 million years. Before Pangaea, there was Pannotia, and before that, Rodinia, and before that, others whose names we may never know because their traces have been erased by time. Pangaea began breaking apart about 200 million years ago. Rifts opened, magma welled up, new ocean basins formed. The Atlantic Ocean did not exist before then. It is still widening today, pushing the Americas away from Europe and Africa at a few centimeters per year. Meanwhile, the Pacific Ocean is shrinking as its edges are consumed at subduction zones. The arrangement of continents affects climate, ocean currents, and the evolution of life. When continents are clustered together, the interior regions become hot and dry, with extreme seasonal temperature swings. When continents are spread out, ocean currents can circulate more freely, moderating global temperatures. The positions of continents also influence where mountains form, where ice sheets develop, and where ocean gateways open or close, all of which feed back into climate. Fossil evidence, rock formations, and the shapes of coastlines all support the reality of continental drift. Identical fossils of ancient plants and animals are found on continents now separated by thousands of kilometers of ocean. Mountain ranges with the same rock types and ages appear on opposite sides of the Atlantic. The fit between the coastlines of South America and Africa is so striking it cannot be coincidence. These observations, first compiled by Alfred Wegener in the early 20th century, were initially met with skepticism because no one could explain how solid continents could plow through solid ocean floor. It was only in the 1960s, with the discovery of seafloor spreading and the development of plate tectonic theory, that the mechanism became clear. Earth's atmosphere has changed dramatically over billions of years. The air we breathe today is very different from Earth's primordial atmosphere. In the beginning, the atmosphere was likely composed of hydrogen and helium captured from the solar nebula. But these light gases quickly escaped to space. As Earth's interior heated and differentiated, volcanic outgassing released a secondary atmosphere rich in water vapor, carbon dioxide, nitrogen, methane, and ammonia. There was no oxygen. The early atmosphere was reducing rather than oxidizing, meaning it would have been toxic to most life forms that exist today. The transformation began with life itself. About 3.5 billion years ago, simple single-celled organisms called cyanobacteria evolved the ability to perform photosynthesis, using sunlight to convert carbon dioxide and water into sugars and oxygen. At first, the oxygen they produced reacted immediately with iron dissolved in the oceans, creating vast deposits of oxidized iron that settled to the seafloor. These ancient banded iron formations, found in rocks around the world, are among the earliest signs of photosynthetic life. For hundreds of millions of years, the oceans and rocks absorbed nearly all the oxygen produced by cyanobacteria. But eventually, around 2.4 billion years ago, oxygen began accumulating in the atmosphere. This event, known as the Great Oxygenation Event, fundamentally changed Earth's surface chemistry and climate. It also caused a mass extinction of anaerobic organisms for whom oxygen was a poison. Yet it paved the way for more complex life. Oxygen allows for aerobic respiration, a far more efficient way of extracting energy from food than the anaerobic pathways available before. Without oxygen, complex multicellular life as we know it could never have evolved. By about 600 million years ago, oxygen levels had risen enough to support the first animals. Today, Earth's atmosphere is about 78% nitrogen, 21% oxygen, and small amounts of argon, carbon dioxide, and trace gases. This composition is maintained by the biosphere. Plants and algae produce oxygen. Animals and decomposers consume it. Volcanic eruptions, weathering of rocks, and human activities add and remove carbon dioxide. The balance is delicate, regulated by biogeochemical cycles operating over timescales from days to millions of years. The atmosphere we often take for granted is not a fixed feature of the planet, but a product of life interacting with geology, constantly evolving, constantly responding to change. Life on Earth began at least 3.5 billion years ago. The exact origin of life remains one of the deepest mysteries in science. We do not know how non-living chemistry first organized itself into living cells capable of metabolism, growth, and reproduction. But we know it happened, and we know it happened early in Earth's history. The oldest widely accepted fossils are stromatolites, layered structures built by communities of microorganisms. These fossils, found in rocks in Australia and southern Africa, are about 3.5 billion years old. They formed in shallow coastal waters where cyanobacteria trapped and bound sediment, layer upon layer, creating structures that still exist today in a few rare environments. Some evidence suggests life may have originated even earlier. Chemical signatures in rocks from Greenland, over 3.7 billion years old, have been interpreted by some scientists as biological in origin, though this remains debated. If life did begin that early, it means it arose almost as soon as conditions on Earth permitted, within a few 100 million years of the surface cooling and oceans forming. Early life was simple. For most of Earth's history, the planet was inhabited only by single-celled organisms. Bacteria and archaea dominated for billions of years, evolving slowly, diversifying into countless forms, inhabiting every available environment, from hot springs to deep ocean sediments. They developed photosynthesis, nitrogen fixation, and countless metabolic pathways that would later support more complex ecosystems. It was not until about 1.8 billion years ago that eukaryotic cells, cells with a nucleus and complex internal structures, first appeared. These cells arose through a process of symbiosis, when one cell engulfed another and the two began living together, eventually becoming inseparable. Mitochondria, the energy-producing organelles in nearly all eukaryotic cells, were once free-living bacteria. Chloroplasts, the photosynthetic organelles in plants and algae, were once cyanobacteria. These mergers were some of the most important events in the history of life, enabling the evolution of complexity. Even then, life remained mostly microscopic for another billion years. The first multicellular organisms, simple assemblages of cells working together, appeared around 600 million years ago. And then, in a geological blink of an eye, life exploded in diversity. The Cambrian explosion, beginning around 540 million years ago, saw the rapid appearance of most major animal groups. Within just a few tens of millions of years, oceans that had been dominated by microbes and simple sponges became filled with arthropods, mollusks, worms, and the ancestors of vertebrates. Since then, life has continued to evolve, adapt, and diversify, filling every corner of the planet. Today, Earth is home to millions of species, from bacteria to blue whales, from fungi to ferns, all descended from those first simple cells that arose in Earth's primordial oceans. Earth is the only known planet with plate tectonics. Among all the rocky planets and moons in our solar system, Earth is unique in having active plate tectonics. Mars shows evidence of ancient volcanism and tectonic activity, but it is now geologically dead, its interior too cold to drive mantle convection. Venus may have some volcanic activity, but its thick, rigid crust does not break into plates. Instead, heat builds up beneath the surface until it erupts catastrophically, resurfacing large areas at once. Earth's plate tectonics requires a specific set of conditions. The planet must be large enough to retain heat and maintain a molten interior. It must have water, which lowers the melting point of rocks and allows the crust to bend and break more easily. It must have the right balance of internal heating from radioactive decay and heat left over from formation. And it must cool at just the right rate, neither too fast nor too slow. Earth happens to meet all these conditions. The result is a surface that is constantly renewing itself, recycling old crust and creating new, distributing heat and material between surface and interior. This process has profound implications for habitability. Plate tectonics regulates atmospheric carbon dioxide over geological timescales through the carbonate-silicate cycle. When carbon dioxide levels rise, the planet warms. Warm temperatures enhance rainfall and weathering of rocks, which draws carbon dioxide out of the atmosphere and into the oceans, where it forms carbonates. These carbonates are eventually subducted into the mantle and released back to the atmosphere through volcanism, completing the cycle. This feedback mechanism acts as a planetary thermostat, preventing Earth from freezing over or overheating over hundreds of millions of years. It is one reason Earth has remained habitable for billions of years, even as the sun has grown brighter over time. Earth is tilted on its axis, giving us seasons. Earth's axis is tilted about 23.5 degrees relative to the plane of its orbit around the sun. This tilt, called obliquity, is what gives us seasons. When the northern hemisphere is tilted toward the sun, it experiences summer, receiving more direct sunlight and longer days. At the same time, the southern hemisphere is tilted away, experiencing winter with shorter days and less intense sunlight. 6 months later, the situation reverses. The tilt is not arbitrary. It is thought to result from the giant impact that formed the Moon, an event that knocked Earth's rotation off vertical and left it spinning at an angle. The exact angle has varied slightly over tens of thousands of years due to gravitational interactions with the Moon and other planets. But it has remained relatively stable thanks to the Moon's stabilizing influence. Without the tilt, there would be no seasons. Every location on Earth would experience the same climate year-round, determined only by latitude. The equator would remain hot, the poles cold, and everywhere in between would see little variation. Life would still exist, but it would be different. Many organisms time their life cycles to the seasons, migrating, breeding, hibernating, or flowering in response to changing temperatures and day lengths. Human agriculture depends heavily on seasonal patterns of temperature and rainfall. The rhythms of life on Earth are woven from the spinning of the planet and the tilt of its axis, small geometric facts with profound consequences. The tilt also creates the phenomenon of polar day and polar night. Near the poles, during summer, the sun does not set for weeks or months. During winter, it does not rise. These extreme light regimes shape unique ecosystems, from the brief explosion of life during the Arctic summer to the deep winter dormancy when nearly all activity ceases. The tilt is a gift, a consequence of ancient violence that brought richness and complexity to life on Earth. A single day on Earth has not always been 24 hours long. When Earth first formed, it rotated much faster than it does today. A day may have been only 5 or 6 hours long. Over billions of years, the planet has been slowing down, and it continues to slow, though the change is almost imperceptible. The primary cause is tidal friction. The Moon's gravity pulls on Earth's oceans, creating bulges of water on the side facing the Moon and the side facing away. As Earth rotates beneath these bulges, friction between the moving water and the ocean floor and coastline dissipates energy, gradually slowing Earth's rotation. At the same time, the Moon drifts slightly farther from Earth each year as angular momentum is transferred from Earth's spin to the Moon's orbit. 400 million years ago, during the Devonian period, when fish were diversifying and plants were colonizing land, a day was about 22 hours long. The Moon was closer, and tides were stronger. If we could travel back to the time of the dinosaurs, we would find days perhaps 23 hours long. The Earth spun a little faster. The Moon hung larger in the sky. If we could go back to the Hadean Eon, shortly after the Moon formed, we would find a world spinning so fast that day and night flickered past in a blur, and the Moon loomed enormous on the horizon, perhaps 10 to 20 times closer than it is now. The length of the day has shaped the evolution of life. Many organisms have internal clocks, circadian rhythms that regulate sleep, metabolism, and behavior on a roughly 24-hour cycle. These rhythms are ancient, present even in cyanobacteria, and they have evolved to match the planet's rotation. As the day lengthens over geological time, life adapts. The relationship between Earth's spin, the Moon's orbit, and the rhythms of life is a deep connection forged over billions of years. Earth's inner core is as hot as the surface of the Sun. At the very center of the planet, nearly 6,400 kilometers beneath the surface, lies the inner core. It is a solid sphere of iron and nickel about the size of the Moon, under such immense pressure that despite temperatures around 5,000 to 6,000 degrees Celsius, it cannot melt. Surrounding it is the outer core, also made of iron and nickel, but in liquid form. This layer is about 2,000 kilometers thick, and its convective motion generates Earth's magnetic field. The heat in Earth's core comes from two main sources. Some is primordial heat, left over from the violent impacts and gravitational compression that formed the planet billions of years ago. The rest comes from the radioactive decay of elements like uranium, thorium, and potassium in the mantle and crust. These elements slowly break down over millions of years, releasing energy. The core's heat drives mantle convection, which in turn drives plate tectonics. It also generates volcanic activity, earthquakes, and mountain building. In a sense, the core is the engine of Earth's geological activity. If it were to cool completely, the planet would become geologically dead, like Mars. The magnetic field would fade, leaving the surface exposed to solar radiation. Plate tectonics would cease, and the slow recycling of carbon that regulates climate would stop. Eventually, Earth would lose its atmosphere and become a barren, lifeless rock. But Earth's core will remain hot for billions of years, sustained by the decay of radioactive elements and the slow cooling of a planet that began its existence in fire. We will never see the core directly. The deepest hole ever drilled, the Kola super-deep borehole in Russia, reached only about 12 kilometers, barely scratching the crust. Everything we know about the core comes from indirect methods: seismic waves from earthquakes, studies of Earth's magnetic field, and comparisons with meteorites thought to represent fragments of planetary interiors. Yet, despite being forever out of reach, the core shapes our world in fundamental ways, a hidden furnace at the heart of the living Earth. The Amazon rainforest produces about 6% of the planet's oxygen. The Amazon is often called the lungs of the Earth, though this metaphor is imperfect. While it is true that the rainforest produces enormous amounts of oxygen through photosynthesis, it also consumes nearly as much through respiration, both from plants at night and from the decomposition of organic matter. The net oxygen contribution is relatively small on a global scale. Most of Earth's atmospheric oxygen comes from oceanic phytoplankton, microscopic algae drifting in the sunlit surface waters. These tiny organisms, though invisible to the naked eye, perform about half of the world's photosynthesis. The Amazon's true importance lies not in oxygen production, but in carbon storage, biodiversity, and climate regulation. The forest contains about 150 billion metric tons of carbon locked in its trees, soils, and plant matter. When forests are cleared or burned, this carbon is released to the atmosphere as carbon dioxide, contributing to climate change. The Amazon also plays a critical role in the water cycle. Trees draw water from the soil and release it through their leaves in a process called transpiration. This moisture rises into the atmosphere, forms clouds, and falls as rain, often hundreds or thousands of kilometers away. The Amazon essentially creates its own weather, recycling water through the forest and influencing rainfall patterns across South America and beyond. The rainforest is home to an estimated 10% of all species on Earth. It harbors countless plants, insects, birds, mammals, reptiles, amphibians, and microorganisms, many of which are found nowhere else. This biodiversity is a reservoir of genetic information, a library of evolutionary solutions to life's challenges. It provides food, medicine, materials, and inspiration. The loss of the Amazon would be a loss for the entire planet. It would release vast amounts of carbon, accelerate climate change, disrupt regional and global weather patterns, and drive countless species to extinction. The Amazon is not humanity's to lose, but it is in our power to protect or destroy. The choice will shape the Earth our descendants inherit. Earth's oceans contain 97% of the planet's water. The ocean is not just a body of water. It is a complex, dynamic system that regulates climate, absorbs carbon dioxide, produces oxygen, and supports an immense diversity of life. The ocean covers 71% of Earth's surface, with an average depth of about 3,700 meters. The deepest point, the Mariana Trench in the Western Pacific, descends to nearly 11,000 meters, deeper than Mount Everest is tall. If you could place the mountain inside the trench, its peak would still be over 2 kilometers underwater. The ocean is divided into layers based on temperature, light, and pressure. The sunlit surface layer, called the euphotic zone, extends down to about 200 meters and is where most photosynthesis occurs. Below this is the twilight zone, where light fades but life persists, adapted to dimness and pressure. Deeper still is the midnight zone, completely dark, cold, and under immense pressure, yet inhabited by strange and fascinating creatures. The ocean floor is not flat. It is a landscape of mountains, valleys, and plains as varied as any continent. Mid-ocean ridges, underwater mountain ranges formed by tectonic spreading, stretch for over 60,000 kilometers, making them the longest mountain chains on Earth. Deep ocean trenches mark subduction zones, where one tectonic plate dives beneath another. Seamounts, underwater volcanoes that do not reach the surface, rise from the abyssal plains, often serving as oases of life in the deep. The ocean is in constant motion. Surface currents, driven by wind, move water across entire ocean basins. The Gulf Stream, for example, carries warm water from the Gulf of Mexico across the Atlantic to northern Europe, moderating the climate and making places like Britain and Norway far warmer than their latitude would suggest. Deeper currents, driven by differences in temperature and salinity, form a global conveyor belt called the thermohaline circulation, moving water between the surface and the deep, transporting heat, nutrients, and dissolved gases. This circulation plays a crucial role in regulating Earth's climate. The ocean absorbs about 30% of the carbon dioxide released by human activities, slowing the pace of climate change, but at a cost. As carbon dioxide dissolves in seawater, it forms carbonic acid, lowering the ocean's pH. This process, called ocean acidification, threatens marine organisms that build shells and skeletons from calcium carbonate, including corals, mollusks, and some plankton. The consequences ripple through food webs, affecting fish, seabirds, and ultimately humans who depend on the ocean for food. The ocean is also a major source of oxygen. Phytoplankton, microscopic photosynthetic organisms drifting in the sunlit surface layer, produce about half of the oxygen in Earth's atmosphere. These tiny beings, invisible to the naked eye, sustain life on land and in the sea. They form the base of the marine food web, feeding zooplankton, which in turn feed fish, which feed larger predators, all the way up to whales and sharks. The ocean is still largely unexplored. We have mapped the surface of the Moon and Mars in greater detail than the ocean floor. Vast areas of the deep sea remain unknown, home to species we have never seen, ecosystems we do not yet understand. The ocean holds mysteries, resources, and lessons we have only begun to uncover. It is a reminder that even on our home planet, there are frontiers still to explore. The Pacific Ocean is so large, it contains more water than all other seas combined. The Pacific covers more than 165 million square kilometers, larger than all the land on Earth put together. It stretches from the Arctic in the north to the Antarctic in the south, from the Americas in the east to Asia and Australia in the west. It is not just the largest ocean, it is the largest feature on the planet. The Pacific is so vast that early Polynesian navigators, without compasses or maps, managed to colonize islands scattered across it over thousands of years. They navigated by stars, wave patterns, bird flight, and oral knowledge passed down through generations. Their voyages rank among the greatest feats of human exploration, crossing thousands of kilometers of open ocean in outrigger canoes to settle places like Hawaii, Easter Island, and New Zealand. The Pacific is rimmed by the Ring of Fire, a zone of intense volcanic and seismic activity. About 75% of the world's active volcanoes are located around the Pacific's edges, and about 90% of the world's earthquakes occur here. This activity is driven by the Pacific Plate and other smaller plates subducting beneath continental plates, creating trenches, volcanic arcs, and mountain ranges. The Pacific Ocean is home to the largest living structure on Earth, the Great Barrier Reef. Stretching over 2,300 kilometers along the coast of Australia, the reef is built by countless tiny coral polyps, each secreting calcium carbonate to form a protective skeleton. Over millions of years, these skeletons accumulate into vast reefs that support extraordinary biodiversity. Fish, crustaceans, mollusks, sea turtles, sharks, rays, and countless other species make their home in the reef's nooks and crannies. The Pacific is also home to the deepest point on Earth, the Challenger Deep in the Mariana Trench. At nearly 11,000 meters below sea level, the pressure is over 1,000 times greater than at the surface. Yet even here, life exists. Amphipods, sea cucumbers, and microorganisms thrive in the cold darkness, adapted to conditions that would crush most life forms. The Pacific has shaped human history and culture. Its islands are home to diverse peoples with rich traditions. Its currents have carried explorers, traders, and migrants. Its resources have fed civilizations, and its vastness reminds us that Earth is a water world, where the ocean, not the land, dominates the surface. Mount Everest is still growing. The Himalayas, the highest mountain range on Earth, continue to rise. Mount Everest, the tallest peak at 8,849 meters above sea level, gains about 4 millimeters in height each year. This growth is driven by the ongoing collision between the Indian and Eurasian tectonic plates. India, once an island continent, has been drifting northward for millions of years. About 50 million years ago, it collided with Eurasia. The collision continues today, pushing rock upward and creating the Himalayas. The mountains grow slowly, but they also erode. Wind, rain, ice, and glaciers wear away the peaks, carving valleys and carrying sediment down to the plains. The balance between uplift and erosion determines the ultimate height of the mountains. In some places, uplift wins and the mountains rise. In others, erosion dominates and peaks are worn down. The Himalayas are not the only mountains on Earth, but they are the youngest and tallest above sea level. Older mountain ranges, like the Appalachians in North America or the Ural Mountains in Russia, were once much taller but have been worn down by hundreds of millions of years of erosion. The rocks that form mountains tell stories of deep time. Fossils of marine organisms are found at the top of Everest, evidence that the rock was once part of an ancient seafloor before being lifted to the roof of the world. Limestone, sandstone, and shale, all formed from sediments deposited in ancient oceans, now cap the highest peaks. Mountains shape climate and ecosystems. They force air to rise, cooling it and causing precipitation on windward slopes. The Himalayas block cold air from the north, keeping the Indian subcontinent warmer than it would otherwise be. They also create rain shadows, areas on the leeward side that receive little precipitation. Mountains are barriers and corridors, isolating some species and connecting others. They create gradients of temperature and moisture, allowing diverse ecosystems to exist within short distances. Climbing Mount Everest is a test of human endurance. The air at the summit contains only a third the oxygen available at sea level. Temperatures can drop to -40 degrees Celsius. Winds can exceed 160 kilometers per hour. Despite these challenges, hundreds of people reach the summit each year, drawn by the allure of standing on the highest point on Earth. Yet the mountain does not belong to climbers. It is a sacred site to the Sherpa people, who call it Chomolungma, Mother Goddess of the world. It is home to unique high-altitude ecosystems, and it is a monument to the restless planet beneath our feet, a place where geology is still writing its story. Antarctica is the coldest, driest, and windiest continent on Earth. At the bottom of the world lies a continent almost entirely covered by ice. Antarctica holds about 90% of the world's ice and 70% of its fresh water. The ice sheet averages nearly 2 kilometers thick and reaches over 4 kilometers at its deepest. Beneath this ice lies a landscape of mountains, valleys, and even lakes, hidden from view. The coldest temperature ever recorded on Earth was at Antarctica's Vostok Station, where the thermometer dropped to -89.2 degrees Celsius in July 1983. Most of the continent is a frozen desert, receiving less precipitation than the Sahara. Yet, Antarctica is not lifeless. Along the coast and on the Antarctic Peninsula, where temperatures are milder, mosses, lichens, and algae cling to rocks. Seals, penguins, and seabirds gather in vast colonies. In the surrounding ocean, krill, tiny shrimp-like crustaceans, swarm in numbers so large they can be seen from space, forming the base of the Antarctic food web and supporting whales, seals, fish, and birds. Beneath the ice, life persists in unexpected places. Lake Vostok, a subglacial lake buried under nearly 4 kilometers of ice, has been isolated from the surface for millions of years. Scientists believe it may harbor unique ecosystems, microorganisms adapted to extreme cold, darkness, and pressure. Other subglacial lakes have been discovered across Antarctica, and some may be connected by rivers flowing beneath the ice. Antarctica is a key player in Earth's climate system. The ice reflects sunlight, helping to cool the planet. The cold, dense water sinking around Antarctica drives deep ocean currents that circulate around the globe. The continent is also sensitive to climate change. Warming temperatures are causing some ice shelves to collapse and glaciers to flow faster into the ocean. If the entire Antarctic ice sheet were to melt, global sea levels would rise by about 60 meters, submerging coastal cities and reshaping continents. Antarctica is governed by the Antarctic Treaty, signed in 1959, which designates the continent as a natural reserve devoted to peace and science. No country owns Antarctica, and military activity is prohibited. Dozens of nations maintain research stations, studying everything from ice cores that preserve ancient climate records to the behavior of penguins to the structure of the universe through neutrino telescopes buried in the ice. Antarctica is a place of extremes, a laboratory for understanding Earth's past and future, a reminder of the planet's capacity for both beauty and harshness. The Sahara Desert was once a green and fertile region. About 10,000 years ago, at the end of the last ice age, the Sahara was not a desert. It was a landscape of lakes, rivers, grasslands, and forests. Hippos and crocodiles lived in rivers that no longer exist. Giraffes, elephants, and antelope roamed the plains. Humans hunted and gathered, and later herded cattle, leaving behind rock art that depicts a world utterly unlike today's Sahara. This greening of the Sahara was driven by changes in Earth's orbit and axial tilt, subtle shifts that altered the distribution of sunlight and the strength of monsoons. When the African monsoon strengthened, it brought rain to regions that are now bone dry. Lakes filled, vegetation spread, life flourished. But the changes that brought the green Sahara also reversed it. As Earth's orbit and tilt continued to evolve, the monsoon weakened, rainfall declined, lakes dried up, Vegetation died back. The desert returned. The transition happened over a few thousand years, relatively quickly in geological terms. The Sahara has oscillated between green and desert many times over the past several million years, driven by these astronomical cycles. Today, the Sahara is the largest hot desert on Earth, covering about 9 million square kilometers. Daytime temperatures can exceed 50 degrees Celsius, and in some areas, rain may not fall for years. Yet life persists. Desert plants like acacias and date palms grow where water is available. Animals like camels, fennec foxes, and various reptiles have adapted to the heat and aridity. Beneath the sand lie ancient aquifers, underground reservoirs of water trapped during wetter periods, some of which are now being tapped for agriculture and drinking water. The Sahara also plays a role in global climate. Dust storms lift fine particles high into the atmosphere, carrying them across the Atlantic to South America, where they fertilize the Amazon rainforest. The desert's heat drives atmospheric circulation patterns that influence weather far beyond Africa. The Sahara is a reminder that Earth's climate is not static. Regions that seem permanent can change profoundly over thousands of years. What is desert today may be green again in the distant future, and what is lush may become barren. Understanding these changes helps us appreciate the planet's dynamism and prepares us for the changes ahead. There are more trees on Earth than stars in the Milky Way. A study published in 2015 estimated there are about 3 trillion trees on Earth. That is roughly 400 trees for every person alive today. In comparison, the Milky Way galaxy contains an estimated 100 to 400 billion stars. Trees outnumber stars, at least from our perspective on this small planet. Trees are among Earth's most important organisms. They produce oxygen, absorb carbon dioxide, provide habitat for countless species, stabilize soil, regulate water cycles, and shape climates. A single large tree can transpire hundreds of liters of water per day, cooling the air and contributing to cloud formation. Forests cover about 30% of Earth's land surface, though this is far less than in the past. Before human agriculture and urbanization, forests were more extensive. Deforestation, driven by logging, farming, and development, has reduced global forest cover significantly, with consequences for biodiversity, climate, and water resources. Different types of forests dominate different climates. Tropical rainforests, found near the equator, are the most biodiverse ecosystems on land, home to more than half of all terrestrial species. Temperate forests, found in mid-latitudes, experience distinct seasons and include deciduous trees that lose their leaves in winter and evergreen conifers. Boreal forests, also called taiga, stretch across northern Canada, Scandinavia, and Russia, dominated by cold-tolerant conifers and home to animals like moose, wolves, and lynx. Trees are also among the oldest and largest living organisms. The oldest known individual tree, a Great Basin bristlecone pine in California, is over 5,000 years old. It was already ancient when the pyramids of Egypt were built. The largest tree by volume is a giant sequoia in California named General Sherman, with a trunk volume of over 1,400 cubic meters. Some trees reproduce clonally, sending up new stems from the same root system. The oldest known clonal colony, a grove of quaking aspens in Utah called Pando, is estimated to be tens of thousands of years old. Trees connect us to deep time. They grow slowly, witness generations, and outlive us. They anchor ecosystems and communities. Sitting beneath a tree, You are under the canopy of an organism that has transformed sunlight and air into wood and leaves, providing shade, oxygen, and beauty. Trees are quiet companions, yet they are essential to life on Earth. Coral reefs cover less than 1% of the ocean floor, but support about 25% of marine species. Reefs are built by tiny animals called coral polyps, each no larger than a fingernail. These polyps secrete calcium carbonate, forming hard skeletons. Over generations, these skeletons accumulate into vast structures. The Great Barrier Reef, the largest coral reef system in the world, stretches over 2,300 kilometers along Australia's northeast coast and can be seen from space. Coral reefs thrive in warm, shallow, clear tropical waters. The corals have a symbiotic relationship with microscopic algae called zooxanthellae that live inside their tissues. The algae photosynthesize, producing sugars that feed the coral. In return, the coral provides the algae with a protected environment and access to sunlight. This partnership allows reefs to grow in nutrient-poor waters where other ecosystems would struggle. Reefs are among the most biodiverse ecosystems on Earth. Fish, crustaceans, mollusks, sponges, sea anemones, sea stars, sea urchins, and countless other species live among the coral. Reefs provide shelter, food, and breeding grounds. They support fisheries that feed hundreds of millions of people. They protect coastlines from storms and erosion. They attract tourism, providing income for coastal communities. But coral reefs are fragile. They are sensitive to temperature, light, and water quality. When stressed by warm water, corals expel their symbiotic algae, losing their color and their primary food source. This is called coral bleaching. If conditions do not improve, the corals die. Bleaching events have become more frequent and severe due to climate change. Overfishing, pollution, and ocean acidification further threaten reefs. Some scientists estimate that if current trends continue, most coral reefs could disappear within this century. Yet, there is hope. Some corals are more resilient than others. Restoration efforts are underway, growing corals in nurseries and transplanting them to damaged reefs. Protecting reefs from local stressors like pollution and overfishing can help them withstand climate change. And reducing greenhouse gas emissions globally can slow warming and give reefs a chance to adapt. Coral reefs are rainforests of the sea, hotspots of life and beauty. Their fate is intertwined with the choices we make about climate, conservation, and our relationship with the ocean. The Earth's crust is thinner than the skin of an apple. If Earth were the size of an apple, its crust would be thinner than the apple's skin. The crust, the outermost solid layer of the planet, ranges from about 5 to 70 kilometers thick. Oceanic crust, formed at mid-ocean ridges, is thinner, averaging about 7 kilometers. Continental crust is thicker, averaging about 35 kilometers, but reaching 70 kilometers beneath mountain ranges like the Himalayas. Beneath the crust lies the mantle, a layer of hot, semi-solid rock extending down to about 2,900 kilometers. The mantle makes up about 84% of Earth's volume. It flows slowly over geological timescales, driven by heat from the core. This flow drives plate tectonics, causing the crust to move, collide, and recycle. Below the mantle lies the core, divided into the outer core, liquid iron and nickel, and the inner core, solid iron and nickel. The core makes up about 15% of Earth's volume, but over 30% of its mass because of its high density. The entire structure, from surface to center, is about 6,371 kilometers to the center of Earth. We have only scratched the surface. The deepest mines reach about 4 kilometers. The deepest boreholes reach about 12 kilometers. Everything below that is known only indirectly, through seismic waves, gravity measurements, and magnetic field studies. The thinness of the crust is humbling. All of human history, all of life, all the oceans and mountains and forests exist within this fragile shell. Beneath it lies a world of heat and pressure and slow motion that shapes the surface but remains forever hidden. We live on the skin of a dynamic planet, a thin layer of rock floating on a sea of molten and semi-molten material, sustained by processes we are only beginning to understand. Earth loses about 90 tons of atmosphere to space every day. High above the surface, where the atmosphere thins and merges with space, molecules of gas drift upward. Some are energized by ultraviolet radiation from the sun, gaining enough speed to escape Earth's gravity and drift away forever. Hydrogen is lost most readily because it is the lightest element. Helium, also light, escapes as well. Heavier molecules like oxygen and nitrogen are held more tightly by gravity and are lost only in tiny amounts. This atmospheric escape has been happening since Earth formed. Early in the planet's history, when the sun was more active and Earth's magnetic field was weaker or absent, atmospheric loss was faster. Mars, smaller and without a strong magnetic field, lost most of its atmosphere this way, leaving it cold, dry, and barren. Earth, protected by its magnetic field and replenished by volcanic outgassing and biological processes, has maintained its atmosphere. 90 tons per day sounds like a lot, but it is negligible compared to the total mass of the atmosphere, about 5 quadrillion tons. At this rate, Earth could lose atmosphere for billions of years without significant change. Still, it is a reminder that nothing on Earth is truly permanent. Even the air we breathe is slowly escaping into space, a molecule at a time, carried away by the solar wind. The loss of lighter elements also changes the composition of the atmosphere over time. Earth's primordial atmosphere, rich in hydrogen and helium, was lost early in its history. The secondary atmosphere, produced by volcanic outgassing and later transformed by life, is what we breathe today. In the distant future, billions of years from now, as the sun ages and grows hotter, atmospheric loss will accelerate. Water vapor will rise into the upper atmosphere, where it will be broken apart by ultraviolet light. Hydrogen will escape, and the oceans will gradually evaporate. Eventually, Earth will lose its water and much of its atmosphere, becoming more like Venus. But that future is so distant, it is beyond the timescale of human or even biological concern. For now, Earth's atmosphere remains thick, breathable, and protective, a gift of geology and life working together. Yellowstone National Park sits atop a supervolcano. Beneath the serene landscapes of Yellowstone, a massive reservoir of magma lies only a few kilometers below the surface. This is the Yellowstone caldera, one of the largest active volcanic systems on Earth. The caldera formed about 640,000 years ago in a colossal eruption that ejected more than 1,000 cubic kilometers of rock, ash, and pumice, blanketing much of North America in volcanic debris. The eruption was so large it left a crater tens of kilometers wide. Yellowstone has erupted 3 times in the past 2 million years. Each eruption was catastrophic, changing the landscape and affecting climate globally. Ash from these eruptions has been found across North America, providing evidence of the scale of the events. Today, the volcano is not dormant, but sleeping. Geysers like Old Faithful, hot springs, fumaroles, and mud pots are all signs of the heat and pressure beneath the surface. Magma heats groundwater, which rises and erupts in geysers or seeps out in hot springs, carrying dissolved minerals that paint the rocks in vivid colors. The ground in parts of Yellowstone rises and falls by several centimeters per year, a process called ground deformation, as magma shifts and accumulates beneath the surface. Will Yellowstone erupt again? Almost certainly, but the timescale is uncertain. The volcano erupts on average every 600,000 to 800,000 years, and it has been about 640,000 years since the last major eruption. However, volcanic eruptions do not follow a strict schedule. The volcano could remain quiet for tens or hundreds of thousands of years, or it could erupt sooner. Most likely, any future activity will be smaller eruptions or lava flows, rather than a cataclysmic supereruption. If a supereruption were to occur, the consequences would be severe. Ash would blanket vast areas, collapsing roofs, contaminating water supplies, and disrupting agriculture. Air travel would halt. Sunlight would be blocked, cooling global temperatures for years, and potentially triggering a volcanic winter. It would be a catastrophe for the United States and a global crisis. But such an event is exceedingly rare, and scientists monitor Yellowstone closely with seismometers, GPS, and other instruments. The U.S. Geological Survey maintains that the probability of a supereruption in any given year is about 1 in 730,000. Far lower than many other natural hazards. Yellowstone reminds us that Earth is a dynamic, sometimes violent planet. Even in places of great beauty, the ground beneath our feet is shaped by forces that can build and destroy. Lightning strikes Earth about 100 times every second. Somewhere on the planet, at any given moment, about 2,000 thunderstorms are in progress. Lightning flashes about 8 million times per day, or roughly 100 times every second. Each flash is a discharge of electricity between clouds or between clouds and the ground, releasing energy equivalent to about 1 billion joules. The temperature of a lightning bolt can reach 30,000 degrees Celsius, 5 times hotter than the surface of the sun. This intense heat causes the air to expand explosively, creating the sound we hear as thunder. Lightning is caused by the buildup of electrical charge within storm clouds. As air currents move water droplets and ice particles up and down within the cloud, they collide and transfer electrons, separating positive and negative charges. The negative charge tends to accumulate at the base of the cloud, while the positive charge gathers at the top. When the difference in charge becomes large enough, it overcomes the resistance of the air, and a lightning bolt forms, equalizing the charge. Most lightning occurs within clouds or between clouds. Only about 1 in 4 lightning bolts strikes the ground. When it does, it follows the path of least resistance, often striking tall objects like trees, towers, or buildings. This is why it is dangerous to be the tallest object in an open area during a thunderstorm. Lightning has shaped human culture and mythology. Ancient peoples attributed lightning to gods, seeing it as a weapon or a sign of divine wrath. Lightning ignites wildfires, which, though destructive, play a role in many ecosystems, clearing underbrush and promoting new growth. Lightning also produces nitrogen compounds that fall to the ground with rain, fertilizing soils. Some scientists believe lightning may have played a role in the origin of life, providing energy for chemical reactions that formed the building blocks of life. Lightning is also beautiful, a reminder of the power of atmospheric processes. Watching a lightning storm, we witness electrical forces that span kilometers, connecting sky and ground in a fleeting, brilliant arc. It is nature showing its energy, uncontained and awe-inspiring. The deepest part of the ocean could fit Mount Everest with room to spare. The Mariana Trench in the western Pacific Ocean is the deepest part of the world's oceans. Its lowest point, the Challenger Deep, lies about 10,924 meters below sea level. Mount Everest, the highest point on land, stands 8,849 meters above sea level. If you could place Everest at the bottom of the Challenger Deep, over 2 kilometers of water would still cover its peak. The pressure at the bottom of the trench is over 1,000 times greater than at sea level, equivalent to having a large elephant standing on your thumbnail. The temperature is just above freezing. There is no sunlight, only complete darkness. Yet life exists, even here. In 1960, two men, Jacques Picard and Don Walsh, descended to the Challenger Deep in the submersible Trieste. Through the small viewport, they observed a flatfish and shrimp-like creatures on the seafloor. Decades later, in 2012, filmmaker James Cameron made a solo dive to the Challenger Deep and collected samples. Scientists have since sent unmanned vehicles to explore the trench, discovering a variety of life forms, including amphipods, sea cucumbers, and microorganisms. These creatures have adapted to extreme pressure by having flexible bodies without gas-filled spaces that would be crushed. Some produce special enzymes that allow their cells to function under pressure. Many feed on organic matter that drifts down from the surface, a slow rain of dead plankton, fish, and whale carcasses that sustains deep-sea ecosystems. The deep ocean is the largest habitat on Earth, yet it is the least explored. We know more about the surface of the Moon than the ocean floor. Vast areas remain unmapped, and new species are discovered regularly. The deep sea holds clues to Earth's geology, climate history, and the potential for life in extreme environments. It may even harbor resources, though exploiting them raises ethical and environmental questions. The Mariana Trench is a reminder of the vastness and mystery of the ocean. It is a place where pressure and darkness have shaped life into forms alien to surface dwellers, a world that challenges our understanding and invites exploration. Earth is 4.54 billion years old, but humans have been here for only about 200,000 years. If Earth's history were compressed into a single year, humans would appear only in the last few minutes before midnight on December 31st. All of recorded human history would fit into the last few seconds. For most of Earth's existence, the planet was inhabited only by microorganisms. Multicellular life appeared only about 600 million years ago. Dinosaurs roamed the Earth from about 230 million to 66 million years ago, a span of over 160 million years. Humans, by comparison, have existed for a tiny fraction of that time. Yet, in that brief span, we have transformed the planet. We have spread across every continent, built cities, cleared forests, farmed vast areas, dammed rivers, and altered the atmosphere by burning fossil fuels. We have driven species to extinction and brought others back from the brink. We have split the atom, walked on the moon, and sent probes beyond the solar system. The scale of human impact has led some scientists to propose that we have entered a new geological epoch, the Anthropocene, defined by human influence on Earth's geology and ecosystems. Evidence of this epoch includes changes in sediment composition, the presence of plastics in rock layers, and shifts in the isotopic composition of carbon due to fossil fuel burning. Whether this epoch is formalized or not, it is clear that humans are now a geological force, capable of altering the planet's trajectory. This realization comes with responsibility. We have the knowledge and tools to understand the consequences of our actions. We can choose to protect ecosystems, reduce pollution, conserve resources, and live sustainably. Or we can continue on a path that degrades the environment, drives species to extinction, and makes the planet less hospitable for future generations. The choice is ours. Earth has been here for 4.5 billion years. It has survived ice ages, volcanic eruptions, asteroid impacts, and mass extinctions. It will endure long after humans are gone. But the Earth we leave behind depends on the choices we make now. We are brief guests on an ancient planet. The question is, what kind of guests we will be. Beneath Antarctica lies a landscape hidden under ice. Antarctica is not just a flat sheet of ice. Beneath the ice lies a continent with mountains, valleys, canyons, and lakes. Some of these features rival the largest on Earth. The Gamburtsev Mountains, buried under more than 3 kilometers of ice in East Antarctica, are a mountain range the size of the Alps. They were unknown until recently, discovered through ice-penetrating radar and seismic surveys. Scientists do not fully understand how these mountains formed or why they remain so high despite being covered in ice for millions of years. Antarctica also hosts over 400 known subglacial lakes. These lakes are kept liquid by a combination of pressure from the ice above and geothermal heat from below. The largest, Lake Vostok, is about the size of Lake Ontario and lies under nearly 4 kilometers of ice. It has been isolated from the surface for at least 14 million years, possibly much longer. Scientists believe it may harbor unique ecosystems, microorganisms that have evolved in isolation, adapted to darkness, cold, and high pressure. Sampling these lakes is a technological challenge. Drilling through several kilometers of ice without contaminating the lake is difficult. But success could provide insights into life in extreme environments, and even inform the search for life on icy moons like Europa or Enceladus, which may have similar subglacial oceans. Antarctica's landscape also includes deep canyons and rifts. One canyon system, discovered beneath the ice sheet, is over 300 kilometers long and up to 3 kilometers deep, comparable to the Grand Canyon. These features were carved by rivers and glaciers millions of years ago, before ice covered the continent. Studying the hidden landscape helps scientists understand how the ice sheet formed and how it might respond to climate change. If warming causes the ice to thin or retreat, these valleys could channel meltwater to the ocean, accelerating ice loss and sea level rise. Antarctica is a frozen world, but beneath the ice lies a dynamic landscape shaped by the same forces that sculpt the rest of Earth. It is a reminder that even in the most extreme environments, the planet remains active, changing, and full of surprises. Earth has experienced 5 major mass extinctions, and we may be in the 6th. A mass extinction is an event in which a significant proportion of species on Earth die out in a relatively short period. The 5 major mass extinctions in Earth's history are the Ordovician-Silurian extinction, about 445 million years ago, which killed about 85% of marine species. The cause is thought to be a combination of climate cooling, glaciation, and sea level changes. The late Devonian extinction, about 375 million years ago, which affected about 75% of species, particularly marine life. The causes are debated, but may include volcanic activity, asteroid impacts, and ocean anoxia. The Permian-Triassic extinction, about 252 million years ago, the most severe extinction event in Earth's history. About 96% of marine species and 70% of terrestrial vertebrate species died. Causes likely include massive volcanic eruptions in Siberia, which released enormous amounts of carbon dioxide, causing warming, ocean acidification, and oxygen depletion. The Triassic-Jurassic extinction, about 201 million years ago, which eliminated about 80% of species. Volcanic activity and climate change are suspected causes. The Cretaceous-Paleogene extinction, about 66 million years ago, which ended the reign of the dinosaurs. About 75% of species went extinct. The primary cause was an asteroid impact in what is now Mexico, combined with volcanic activity in India. After each mass extinction, life rebounded. New species evolved to fill the empty niches. Biodiversity eventually recovered, though it took millions of years. Extinctions opened opportunities for other groups to diversify. Mammals, which had been small and relatively insignificant during the age of dinosaurs, radiated into the ecological roles left vacant by the dinosaurs' demise. Today, species are going extinct at rates estimated to be 100 to 1,000 times higher than the natural background rate. Habitat destruction, climate change, pollution, overfishing, and the introduction of invasive species are driving this loss. Some scientists argue we are entering a sixth mass extinction, caused not by asteroids or volcanoes, but by human activity. The consequences of biodiversity loss are profound. Ecosystems become less stable, less able to provide services like clean water, pollination, and carbon storage. The genetic diversity needed for crops and medicines is lost. The web of life frays with unpredictable effects. Unlike past extinctions, we have the knowledge and ability to prevent this one. Conservation efforts, habitat protection, pollution reduction, and addressing climate change can slow and even reverse biodiversity loss. The question is whether we have the will to act. Beneath our feet are rocks that remember ancient climates. Rocks are not just inert material. They are archives, recording the conditions under which they formed. Sedimentary rocks, formed from particles that settled in water or were carried by wind, preserve clues about past environments. Limestone forms in warm, shallow seas. Sandstone can indicate deserts or beaches. Shale forms from fine mud in calm, deep water. The fossils within these rocks tell us what organisms lived and what the climate was like. Ice cores drilled from glaciers in Greenland and Antarctica contain air bubbles trapped as snow accumulated and compressed into ice. These bubbles preserve samples of Earth's ancient atmosphere, allowing scientists to measure carbon dioxide levels, methane concentrations, and temperature proxies going back hundreds of thousands of years. Tree rings record annual growth. Wide rings indicate years with favorable conditions. Narrow rings indicate stress from drought or cold. By studying ancient trees and fossilized wood, scientists can reconstruct climate going back thousands of years. Coral skeletons, ocean sediments, cave formations, all hold chemical signatures that reveal temperature, precipitation, ocean chemistry, and more. By piecing together these records, scientists have reconstructed Earth's climate history. They have identified ice ages, warm periods, rapid shifts, and gradual changes. They have learned that Earth's climate is sensitive to small changes in factors like greenhouse gas concentrations, solar output, and volcanic activity. This understanding is essential for predicting future climate. The past is not just history, it is a laboratory. By studying how Earth's climate responded to changes in the past, scientists can test and refine models, improving predictions of future climate under different scenarios. The rocks beneath our feet hold lessons for the future. Earth's rotation is gradually slowing, and days are getting longer. 4 billion years ago, a day on Earth lasted only about 6 hours. The Moon was much closer, and its gravitational pull on Earth's oceans created enormous tides. As Earth rotated beneath these tidal bulges, friction between the water and the seafloor dissipated energy, gradually slowing the planet's spin. Simultaneously, angular momentum was transferred from Earth's rotation to the Moon's orbit, causing the Moon to spiral slowly outward. This process continues today, though the effect is smaller because the Moon is now farther away and tides are weaker. Earth's rotation slows by about 1.7 milliseconds per century. It is a tiny amount, imperceptible in a human lifetime. But over millions of years, it adds up. In the age of the dinosaurs, a day was about 23 hours long. When the first animals crawled onto land, a day was perhaps 21 or 22 hours long. As days lengthen, the Moon continues to recede, moving about 3.8 centimeters farther from Earth each year. Eventually, billions of years from now, Earth's rotation will slow enough that it becomes tidally locked to the Moon, just as the Moon is tidally locked to Earth. When this happens, one side of Earth will always face the Moon, and a day will last about 47 current days. But this distant future is so far away that the Sun will have changed dramatically by then, likely rendering Earth uninhabitable long before tidal locking occurs. The gradual slowing of Earth's rotation has practical consequences. To keep our clocks in sync with Earth's rotation, scientists occasionally add leap seconds to Coordinated Universal Time, the global time standard. These adjustments account for the small variations in the length of the day. The slowing of Earth is a reminder that even the most fundamental aspects of our planet, the length of a day, the distance to the Moon, are not fixed but are slowly evolving over deep time. More than 80% of the ocean is unexplored and unmapped. Despite living on a water planet, humans know surprisingly little about the ocean. We have detailed maps of Mars, the Moon, and Venus, created using satellites and orbiters. But mapping the ocean floor is more difficult. Water absorbs and scatters light, making optical imaging useless beyond shallow depths. Sonar, which uses sound waves, is the primary tool for mapping the seafloor, but it requires ships to travel slowly over vast areas, a time-consuming and expensive process. As a result, only about 20% of the ocean floor has been mapped in high resolution. The rest is known only in broad outline, based on satellite measurements of the sea surface, which detect subtle variations in gravity caused by underwater features. The deep ocean remains largely unexplored. Only a handful of people have visited the deepest parts, and most of the deep sea floor has never been seen by human eyes. Unmanned submersibles and remotely operated vehicles have explored small portions, revealing bizarre and beautiful life forms, underwater volcanoes, hydrothermal vents, and ecosystems that thrive in complete darkness. Hydrothermal vents, discovered in the 1970s, are openings in the seafloor where superheated water rich in minerals erupts from beneath the crust. Around these vents, entire ecosystems exist without sunlight, powered by chemosynthesis rather than photosynthesis. Bacteria convert chemicals like hydrogen sulfide into energy, forming the base of a food web that includes tube worms, clams, crabs, and fish. These discoveries changed our understanding of where and how life can exist. The ocean likely holds countless species yet to be discovered. New species are found regularly, from tiny microbes to large fish. Some are bizarre, like the barrel-eye fish with its transparent head, or the goblin shark with its protruding jaw. Others are beautiful, like bioluminescent jellyfish that glow in the dark. Exploring the ocean is important for understanding Earth's biodiversity, geology, and climate. The ocean plays a critical role in regulating temperature, storing carbon, and supporting life. Understanding it better will help us protect it and address challenges like climate change, overfishing, and pollution. Earth is the only planet we know with liquid water on its surface. Water exists in solid, liquid, and gas forms throughout the solar system. Ice is common on moons and in comets. Water vapor is present in the atmospheres of several planets. But liquid water on the surface, stable over geological time, is found only on Earth. This is because Earth's temperature and pressure are just right. The temperature is warm enough to keep water liquid and cold enough to prevent it from boiling away. The atmospheric pressure is high enough to allow liquid water to exist at the surface. Mars has ice at its poles and possibly briny liquid water underground. But its thin atmosphere and cold temperatures mean liquid water cannot persist on the surface. Venus is far too hot. The gas giants and their moons are too cold or lack solid surfaces. Some moons, like Europa and Enceladus, may have liquid water oceans beneath thick ice crusts, but not on the surface. Liquid water is essential for life as we know it. It is a solvent, allowing chemicals to dissolve and react. It remains liquid over a wide range of temperatures. It has unique properties, like expanding when it freezes, which allows ice to float and insulates the water below, protecting aquatic life during winter. The presence of liquid water on Earth's surface for billions of years has allowed life to originate, evolve, and diversify. Oceans provided a stable environment for early life. Rivers and lakes have shaped landscapes and ecosystems. Water regulates climate, transports nutrients, and connects disparate parts of the planet. The search for life elsewhere often focuses on the search for water. Missions to Mars look for evidence of past or present water. Telescopes search for exoplanets in the habitable zones of their stars, where temperatures might allow liquid water. The discovery of liquid water on another world would be one of the most profound findings in human history. For now, Earth remains the only known water world, a precious anomaly in a solar system of extremes. The boundary between Earth's atmosphere and space is gradual, not sharp. There is no clear line where the atmosphere ends and space begins. The atmosphere simply becomes thinner and thinner with altitude until it merges with the near vacuum of space. For practical purposes, the Kármán line at 100 kilometers altitude is often used as the boundary. Above this altitude, the air is so thin that aircraft cannot generate enough lift to fly, and spacecraft do not experience significant atmospheric drag. But even above the Kármán line, trace amounts of atmosphere persist. The International Space Station orbits at about 400 kilometers altitude, but it still experiences enough atmospheric drag to require periodic boosts to maintain its orbit. Satellites in low Earth orbit gradually lose altitude due to drag and eventually burn up in the atmosphere if their orbits are not maintained. At higher altitudes, the atmosphere becomes even thinner. The exosphere, the outermost layer, extends from about 700 kilometers to 10,000 kilometers or more. Here, individual atoms and molecules can travel hundreds of kilometers without colliding with each other. Some escape to space, others fall back toward Earth. The atmosphere at these altitudes is shaped by the solar wind and Earth's magnetic field, creating regions like the ionosphere, where charged particles interact with radio waves, and the magnetosphere, where Earth's magnetic field deflects solar wind and traps radiation in belts around the planet. The gradual transition from atmosphere to space reflects the nature of gases. There is no solid boundary, only a progressive thinning as gravity's hold weakens and molecules drift farther apart. This gradual transition is true of other planets as well. Understanding where the atmosphere ends is important for space travel, satellite operations, and understanding how Earth interacts with space. But it also reminds us that Earth is not isolated. It exists in a cosmic environment, bathed in solar radiation, surrounded by a magnetic field, losing a little atmosphere to space while gaining a little cosmic dust from space. Earth is part of the solar system, connected to the sun and the void beyond. Thank you for drifting through the quiet story of Earth tonight. We have wandered across deep time and vast distances, from the molten birth of a planet to the delicate balance of ecosystems, from the crushing depths of ocean trenches to the thin veil of atmosphere that separates us from space. We have seen how continents drift, how oceans breathe, how life has transformed the planet and been transformed by it. We have marveled at the forces that shape mountains, split continents, and spin hurricanes. And we have remembered that this pale blue dot, so small and fragile in the vastness of space, is the only home we have ever known. Earth is ancient, dynamic, and resilient. It has endured countless changes, catastrophes, and transformations. Yet, it is also delicate, its habitability maintained by a web of interconnected processes that can be disrupted by forces both natural and human. We are part of this planet, not separate from it. Our lives are woven into its systems, dependent on its air, water, soil, and the countless species with which we share it. As you rest tonight, let the weight of the world fall away. You are lying on a planet that spins through space at over 1,600 kilometers per hour, orbiting a star at over 100,000 kilometers per hour, circling the galaxy at hundreds of thousands of kilometers per hour. Yet you feel none of this motion. The ground is steady beneath you. The air is still and breathable. The night is calm. Earth cradles you, as it has cradled all life for billions of years. If these quiet journeys into wonder brought you peace, consider liking, subscribing, or sharing a thought below. It helps others find their way here, one sleepy soul at a time. But for now, let your thoughts drift like clouds. Let your breathing slow like the patient turning of the tides. You have done enough for today. The earth will keep spinning. The stars will keep shining. The oceans will keep breathing. And you, for now, can simply rest. Close your eyes and dream of ancient forests and deep oceans, of mountains rising and stars wheeling overhead, of a planet alive with motion and light. Dream of Earth, your home, turning slowly in the endless dark. Good night.